The Engineering of Large Software Systems, Week 10, Life Cycle Considerations and the Integration of Systems and Software Engineering. This lecture addresses two critical issues that bridge strategy and tactics: system life cycles and the need for integrating or reconciling systems and software engineering. As these paintings from Thomas Cole's The Voyage of Life depict, the first issue addresses the life cycle chosen for the large software system development and the way we plan and execute the project within that life cycle. The selection of a life cycle model may seem to be something left to the customer or the executive level, but the wrong life cycle philosophy and implementation can mean disaster to a large software system. Essentially, the life cycle model is the framework for the activities we undertake in creating, deploying, operating, and retiring the software system we are responsible for. To start what is a serious discussion, here's a somewhat lighthearted view of life cycle from a commercial source. While every life cycle model has common factors, there are a number of approaches to defining the activities and phases, and life cycle models for systems and software tend to be similar. We have seen that change is inevitable in large system developments, so the life cycle models we select should recognize variability and facilitate the project's ability to adapt to that change. We have also seen that system development is a learning process, and so the life cycle model should support knowledge management. Typically, a project begins with lots of uncertainty, lots of opportunity for change. This is good since it opens up the possibility of high value from creativity and discovering new ways to deliver capabilities. However, over time, as the system is being constructed and delivered, we need to reduce uncertainty and the amount of change we face. But uncertainty and change never go away. We need to constantly manage with that fact in mind. As an example, the waterfall life cycle model is a step-by-step approach often applied in traditional project management. It is generally implemented as a once-through sequence of requirements definition, design, construction, validation, delivery, and sustainment. The waterfall requires that we know a great deal early on and assumes little unpredictable variation. The philosophy is to plan in detail, make decisions to reduce variability, and stick to them. Because of this, there is no real mechanism to revisit any of the phases should significant changes occur. So, in large projects, where change does occur over time, the cone of uncertainty begins to reverse its trend. When that happens, either the system delivered no longer meets the needs of the customer, or the rework required to accommodate the changes grows to the point that project success becomes impossible within a reasonable approximation of the projected budget and schedule. Software developers have increasingly adopted the BAME concept of a spiral model that is specifically designed to support the learning required in software systems. Spiral is only one of several approaches, including incremental and iterative, but its core philosophy of risk-driven decision-making, evolution, and iterative development does support the change expected in large system developments. One life cycle analogy that has been applied to the development of large systems is that of the military combat discipline called C4ISR, for command, control, communication, computers, intelligence, surveillance, and reconnaissance. C4ISR tenets include the idea of continuous planning, the application of observe, orient, decide, act, or OODA loops, and the mixture of rapid adaptability along with stable operations goals. For example, you have to take out an enemy capability, but the weather may change your tactics. Here's an illustration of how the OODA loop maps into a spiral life cycle. The latest thinking in large systems life cycles, actually an extension of the original spiral approach, is called the Incremental Commitment Model, or ICM. Developed by Barry Boehm and others, the ICM integrates hardware, software, and human factors elements of systems engineering and addresses the need for synchronization and stabilization in systems artifacts as they evolve concurrently. It attempts to build on the strengths of previous life cycle models and avoid their weaknesses. The ICM is not a specific life cycle. It is a risk-driven framework for tailoring system life cycle processes. Like Spiral, it uses risk to determine how much process agility or rigor is enough to satisfy the system's objectives subject to its constraints. This can vary across different parts of the system, depending on the risks associated with the various parts. The ICM is best defined by its 6 core principles. 1. Commitment and accountability of system sponsors. 2. Success-critical stakeholder satisficing. 3. Incremental growth of system definition and stakeholder commitment. 4. Concurrent engineering. 5. Iterative development cycles. And 6. Risk-based activity levels and milestones. This overview of the ICM shows how it spans the life cycle process from concept exploration to operations. Each phase culminates with an evidence-based anchor point milestone review. At each anchor point, there are 4 options based on the assessed risk of the proposed system. These options result in many possible process paths, some of which involve revisiting earlier work. The life cycle phases are organized into 2 stages: system definition and system development and operations. As shown, ICM is designed so that activities can evolve concurrently, although the level of activity can vary across the life cycle. Key to the stabilization is the use of evidence-based milestone reviews. These are addressed more fully in Barry's video, which you can watch after this lecture. Gambling provides a good analogy to the philosophy behind the ICM. Traditional life cycles involve total commitment to a set of requirements or performance parameters, much like the betting in roulette. Pick a number, spin the wheel, roll the ball. Some number comes up, you either win or you lose. The ICM is more like poker or blackjack. In these games, you look at your initial cards. Then, as you are dealt other cards, you can adapt your betting as you learn more about the probability of success. Can I get to that straight flush, or is 2 pair about all I can do? Let's look at an example from the experience of remotely piloted vehicles, or RPVs, that are becoming more and more a part of hazard control, reconnaissance, and intelligence activities. This is a hypothetical case, but it illustrates the difference between total commitment and incremental commitment, and also shows the value of competitive prototyping. RPVs are airplanes or helicopters operated remotely and designed to keep humans out of harm's way. Current RPV systems are human-intensive, often requiring 2 people to operate a single vehicle. Given increasing demand, there is a strong desire to modify the 1 vehicle controlled by 2 people ratio to allow for a single operator to operate more than 1 RPV. In our hypothetical case, an experimental proof-of-principle prototype has been developed and has demonstrated the possibility of using agent-based technology to allow a single operator to control 4 RPVs. That's a 4-to-1 RPV to human ratio. Let's look at how this demonstration might be used to develop a system under each approach. First, we'll look at the results from a traditional total commitment approach. The demonstration results and a number of assumptions were used to create a proposed program to develop the 4-to-1 ratio system at an optimistic cost of $1 billion and a schedule of 40 months. A request for proposal was sent out to prospective bidders. The winning bidder provided an even more impressive demonstration of agent technology and a proposal indicating that all of the problems were well understood, that a preliminary design review could be held in 120 days, and that the cost would be only $800 million. At the PDR, however, the contractor could not show feasible solutions for several key scenarios, but since the schedule was tight and the contractor provided ideas for addressing the problems, the PDR was declared to be passed. Unfortunately, the problems were individually more complex than expected and jointly coupled in critical ways, and after 40 months and $800,000, the components developed were experiencing integration problems. Eventually, at the end, a reduced 1-to-1 capability was achieved and the system delivered, but only after 80 months and a cost of over $3 billion. Now let's look at how we would apply the incremental commitment approach. In this case, the project began by investing $25 million in a more detailed exploration phase to determine key performance parameters and develop operational scenarios, including inconsistent data, operator collaboration, and interoperability scenarios. It also developed evaluation criteria and processes. Based on the exploration results, 4 bidders were selected to develop virtual prototypes to address the key issues and provide evidence of the level of performance. The program office engaged a set of independent experts to evaluate the bidders' results. The evaluation showed that the prospects for developing a 4-to-1 capability were clearly unrealistic, but that achieving a 1-to-1 capability was sufficiently probable to merit another level of investment. This next phase was funded at $75 million. Some of the more ambitious key performance parameters were scaled back, and the competing contractors were reduced to 3 and tasked to develop more detailed prototypes. The new prototypes provided sufficient evidence of feasibility that $225 million was provided to support the 2 top competitors in a technology development or foundations phase. These 2 competitors developed operational prototypes and provided evidence of their ability to satisfy the key performance parameters and scenarios. They also developed the foundation artifacts for a successful engineering and manufacturing development phase. The feasibility evidence included a few shortfalls, but each was covered by a specific risk mitigation plan. The winners proposed $675 million 18-month 3-increment plan to develop an initial operational capability was adopted. The initial system was delivered on budget and schedule, with a few lower priority features deferred to later systems increments. The result was $1 billion spent over 42 months. So, how do we compare these? Well, by buying information early, the incremental commitment and competitive prototyping approach was able to develop a system with much less late rework than the total commitment approach, and with much more visibility and control over the process. While the competitive prototyping approach spent about $150 million on unused prototypes, its overall expenditure was only $1 billion, a third of the $3 billion for the total commitment approach. It also delivered the capability in half the time, yielding a very strong return on investment. Finally, because the customer had more realistic expectations, the 1-to-1 capability delivered was viewed as a major success, rather than a disappointing shortfall from the promised 4-to-1 capability in the total commitment approach. The ICM addresses many of the challenges of large, complex system development by integrating spiral and agile concepts into the life cycle. It also provides a way of tailoring that life cycle to better adapt to the changing nature and evolving risks associated with large system development. However, implementing ICM has significant implications for traditional infrastructure and will require changing the way much of that work is performed. Our second topic involves resolving the differences between 2 key disciplines required in developing large systems: software engineering and systems engineering. The need for reconciling these disciplines results from our earlier discussion about interdependent systems. Remember that they are systems where the system and software design efforts are so interrelated that they must be accomplished concurrently and collaboratively. We stated that implementing the ICM would need changes in traditional thinking. Integrating software and systems engineering has the same set of issues. These are just a few of the amazing number of unresolved problems, undefined topics, and general barriers to successful or even viable integration. However, some intrepid explorers, namely Art Peister and Rich Turner, have dared to at least set out a possible approach to begin this process. They have defined a simple framework that they believe describes the critical aspects of this problem and will help address the 4 key integration issues of vocabulary, measurement, entanglement, and value. Called Touchpoint, the framework comprises 4 fundamental components: processes, touchpoints, faults, and resolution strategies. The processes of systems and software engineering are very similar, as evidenced by the harmonization of ISO IEC 15288 as a single definition of systems and software engineering processes. Their assumption is that given this similarity, there should be a way to identify where the process activities for each discipline interact in such a way as to positively or negatively affect program risk or value. That definition of a touchpoint is the foundation of the framework. For each touchpoint identified, there is a possibility that the activities as defined do not produce the desired results, and so fail to produce maximum value due to some fault in the interaction at the touchpoint. Such faults can occur in 3 basic categories: gaps, where something that should happen doesn't happen; waste, where something is done more than once in essentially the same manner; and clashes, where the activities produce conflicting or incompatible results or actions. Clashes can be due to vocabulary, values, or mental models. Resolution strategies are ways in which faults can be eliminated or minimized. There may be many resolution strategies for any one fault. While initial pilot activity has shown that this touchpoint framework is promising, much work remains to actually identify a critical mass of touchpoints and their related data, and to create tools to support applying the insight gained to real programs. However, even without a codified set of interactions, it is essential that large system developments focus energy on the collaboration and concurrency of the systems engineering and software engineering activities. As we will see later, this can be accomplished through organizational structure, management decisions and planning, and technical processes. Lifecycle models and lifecycle decisions also affect how easily systems and software engineering can be integrated. The ICM provides a good foundation for identifying critical touchpoints, and its emphasis on risk makes it particularly useful in large system development. Finally, since both the ICM and touchpoints involve fundamentally changing the way work is done, remember the quote from Machiavelli we used in describing process change: "Nothing is harder than creating a new order of things."